Now, for optimization algorithms determine if we are going to have a negative probability or a positive probability based on the input of the data in respect to the weights and biases. This is a separate calculation from the activation function. Right here. Optimization algorithms play a significant role in shaping the behavior. So they shape the behavior of neurons within a network, ultimately just grouping them together between negative and positive probabilities. They guide the learning process by adjusting weights which indirectly affect the probabilities associated with neuron activities to determine if a positive or negative probability is occurring. And these probabilities can be thought of as the likelihood of a neuron producing a positive or negative output. So we are just grouping probabilities together. Through the iterative process of training, optimization algorithms group neurons together based on their behavior, influencing whether they tend to produce positive or negative probabilities, and this grouping is essential for the network to learn and make accurate predictions. Overall, with respect to the weights and biases from the parameters set by the model, we're able to understand the network's overall performance. So, and also for further context as well, optimization algorithms are widely used, especially in a method called backpropagation, which we will cover in a future video focusing on the training of neural networks. But right now we're just focusing on the overall structure behind the process of a neural network prior to going further depth in the training. But again, for future reference, we will have that video. And common optimization algorithms used for the process would be gradient descent, stochastic gradient descent, mini-batch gradient descent, ADAM, which stands for adaptive moment estimation, RMS prop, which means the root mean square propagation, autograd, which means adaptive gradient, delta, adaptive gradient delta, and improvement over autograd, and NADAM, which stands for Nesterov accelerated adaptive moment estimation. And we have the following acronym over here. Now, to be able to go over and understand further in depth between gradient descent is a first-order iterative optimization algorithm used to find the local minimum of a differentiable function. The idea is to take small proportional steps in the direction of the negative gradient, the steepest descent, of the objective function with respect to the model parameters. So we are looking for the steepest descent of the objective function and this is technically called gradient descent because it uses the information of the gradient, the steepness of our given slope, to decide the direction, and descent because it aims to descend to the lowest point. So it is descending to the lowest point. As well. And the learning rate defines the size of these steps, and choosing the right learning rate is crucial, as too small of a rate can lead to slow convergence. Also, we have to be crucial about the learning rate to avoid slow convergence. And if we have too large of a gradient descent, that means we would overshoot. the output. There we go. And to be able to break down how the formula is actually built and constructed, so theta refers to the parameter vector of the model, which needs to be optimized. And the following symbol refers to the learning rate, which controls the size of the steps taken towards a minimum loss function. So controls the size of steps taken forward to minimize, or to the minimum of the loss function. And this following group over here, J theta, refers to the gradient of the loss function, referred to as J, with respect to the parameter vector. Respect to the parameter vector. One second. And now let's over to stochastic gradient descent. And so yeah, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.